In 2023, a New York lawyer filed a legal brief written with ChatGPT. It cited 6 court cases with names, dates, case numbers, and quotes from the judges, all perfectly formatted. When the opposing side went looking, they found nothing. All 6 cases were invented. The lawyer was sanctioned, and the story made headlines around the world. But the most important detail usually gets left out. The model was not lying, and nothing inside it broke. It produced those fake cases while working exactly as designed. Over the next few minutes, you will see why the most fluent answer and the true answer are 2 different targets, why invented facts sound so convincing, and what actually reduces the risk. It starts with a quick look at the engine. The engine does one thing. A language model reads the text so far and predicts the next small chunk of text, called a token. For every token it could output, it computes a probability. The likeliest continuations rise to the top of the list. One gets picked, it is attached to the end, and the loop runs again. Your whole answer is built this way, 1 token at a time. Now notice the word that never appears in that description: verify. At no point does anything compare the output against the world. The model scores how well each continuation matches the patterns in the text it trained on. Plausible is the target. True is not a separate input. Most of the time the 2 overlap, because true statements are common in human writing. But they are 2 different things, and the gap between them was built in from the first day of training. Training rewarded exactly 1 skill. The model was shown real sentences with the ending hidden, and scored on how well it predicted the missing words. Guesses that sounded like real text, well-formed, on topic, natural, scored high. Now compare 2 continuations of the same sentence. A plane, correct 1. The bridge was completed in 1932. A smoother, wrong 1. The bridge, completed in 1928, quickly became a beloved landmark. If the wrong version reads more like typical writing, it can score just as well, or even better. Nothing in the training objective says the date must be right. It says the sentence must be likely. Fluency was the goal, and the model got astonishingly good at it. Facts came along for the ride, but only as far as they help prediction. So where do the facts actually live? Not in a database. There is no table inside the model with a row for every bridge and its opening date. Everything it can tell you is compressed into the weights, billions of numbers tuned during training. And compression has a price. A fact repeated millions of times across the training text, like Paris is the capital of France, gets pressed into the weights so firmly that the right continuation wins by a landslide every time. Call it a sharp memory. A fact that appeared only a handful of times, the birth year of a minor poet, the middle author on 1 obscure paper, leaves a faint statistical smudge. A blurry memory. And blurry is dangerous, because blurry does not look empty. The blur still holds the shape of an answer, a plausible-sounding name, a year in the right decade. The exact value is lost. The pattern survives. Now feed a blurry question into the generation loop. The loop has 1 hard rule. It must output a next token at every step. There is no file not found, no empty result, no built-in way to stop and abstain. So when your question points at a blurry region of the weights, the model does the only thing it can do. It outputs the most plausible token anyway. Ask for a citation it never stored sharply, and out comes the shape of a citation. A name-shaped name. A title that sounds like titles in that field. A date-shaped date, and a page number in a sensible range. Every piece is drawn from the pattern of a million real citations, so the assembled result looks flawless. That is exactly what happened to the lawyer. 6 case-shaped cases, generated to fill the place where 6 real memories should have been. You might expect an invented answer to at least sound different. Hesitant, maybe, or vague. It does not. Put a true answer and a false one side by side, and the phrasing is identical. The same assured tone, the same clean structure, the same specific detail. The reason is simple. Tone is not a report on what the model has stored. Tone is just more next token prediction. The training text is full of confident declarative sentences, so confident declarative sentences are what the model writes, whether the fact underneath is sharp or blurry. The confidence is a style it learned from us, not a measurement of evidence. You cannot read truth off the surface of an answer because the surface is generated the same way either way. Some questions are much riskier than others, and the pattern is predictable. Risk climbs with precision. A broad question, like how does photosynthesis work, rests on millions of overlapping training examples. A precise ask, an exact number, a direct quote, a web address, a citation, demands one exact token in a spot where many candidates look equally plausible. Risk climbs on niche topics, because thin training data leaves blurry weights. And risk climbs with length, for a mechanical reason. Every token the model generates becomes input for its next step. If one wrong detail appears early, the loop treats it as established context and builds on it. An invented author acquires a book, then a career, then a famous rivalry. Each step is a perfectly plausible continuation of the last, so the story stays self-consistent. And self-consistent is exactly what convincing looks like. Which raises the obvious question, why not just say, I do not know? Two forces work against it. The first is the training text itself. People mostly write about a topic because they know something about it. So for any question, the internet holds thousands of confident answers and almost no essays saying I have no idea. That makes I do not know a rare continuation, and rare continuations lose the probability contest. The second force is feedback training. Human reviewers rank candidate replies, and a detailed, confident, helpful-sounding answer tends to outrank a cautious hedge, unless the reviewer spots the error. Plausible errors are exactly the ones reviewers miss. Both forces push the same direction, toward answering fluently every time. Declining was never really on the menu. So what actually reduces the risk? Grounding beats memory. Paste the document, the email, the report into the chat, and ask about that. Now the facts sit directly in the model's context window, where it can read them, and the answer is assembled from visible text instead of reconstructed from blurry weights. Accuracy jumps. The same logic powers tools that search the web first and write second. Retrieved sources pin the answer down. Next, ask for checkable sources and actually check one. A fabricated citation rarely survives 30 seconds of searching. And for everything else, one habit covers you. Verify every specific you plan to rely on. Names, numbers, dates, quotes, links. Use the model freely where fluency is the product. Drafting, rewriting, structuring, explaining, brainstorming. Treat every unverified specific as a placeholder until you have checked it somewhere the model cannot touch. Put it all together, and hallucination stops being a mystery. The model is a machine for the most plausible next token. Plausible usually overlaps with true, but nothing inside enforces the overlap. Frequent facts are sharp, rare facts are blurry. The loop must always produce something, and the confident tone is a style, not a signal. No part of that is a malfunction. It is the design working. So split your trust in two. Trust the fluency. Let the model draft, rewrite, summarize, and explain. Verify the specifics. Check every fact that has to be right before it leaves your hands. That split is how you get the machine's real value without inheriting its inventions. Next time, prompting. How to phrase what you ask, so the model actually does what you want, and why small changes in wording change everything.